Out there, in the cold, silent theatre of the cosmos, a darkness stretches between the stars, so complete and so ancient it defies human comprehension. It is a realm of unimaginable distances, a cosmic ocean where our solar system is but a single, luminous island in an endless archipelago of night. For uncounted millennia, this void has been the keeper of secrets, a celestial graveyard for the primordial material left over from the dawn of creation. From this profound emptiness, visitors sometimes emerge. They are silent travellers, ghosts of frozen gas and primordial dust, drifting for eons through a darkness so profound that our concept of time itself loses all meaning. These are the comets, the Oort cloud's forgotten children, sent on long, looping journeys into the inner solar system by gravitational nudges from passing stars. Most arrive and depart unnoticed, faint smudges in the eyepieces of powerful telescopes, but every so often one arrives with a promise. A promise of grandeur, of a spectacle not seen in a lifetime. In the winter of 2019, such a messenger appeared. It was designated C/2019Y4, but we would come to know it by a simpler, more resonant name, Atlas. It was discovered, as so many of these objects now are, not by a lone astronomer peering through a brass telescope on a cold night, but by a tireless robotic sentinel. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, is a pair of telescopes in Hawaii, scanning the entire sky every few nights. Their primary mission is planetary defense, a sleepless watch for asteroids on a collision course with Earth. On December 28, 2019, the system flagged a faint new point of light. It was impossibly dim, 1,000,000 times fainter than the faintest star visible to the naked eye, moving with a purpose against the stellar backdrop. Initial calculations of its trajectory were routine, another faint comet from the outer dark. But as more observations trickled in from observatories around the globe, a breathtaking picture began to form. This was no ordinary celestial nomad. Its orbit was immense, a vast sweeping ellipse that took it on a journey lasting over 4,000 years. It was a long-period comet, a true relic from the solar system's infancy. More intriguing still, its path through the heavens was almost identical to that of the Great Comet of 1844, leading astronomers to a startling conclusion. Atlas was likely a fragment of a much larger, ancient parent body that had shattered on a previous pass through the solar system centuries ago. This lineage was the first hint of its dramatic potential. If its long-lost sibling could put on such a magnificent show, what might Atlas have in store for us? The early signs were more than just promising, they were electrifying. As Atlas fell toward the sun, its temperature began to rise. The ancient ices locked within its nucleus, water, carbon dioxide, ammonia, began to sublimate, turning directly from solid to gas. This process, a form of celestial exhalation, created a vast glowing atmosphere around the solid core called a coma. And Atlas's coma was growing at an astonishing rate. By early 2020, the comet was brightening faster than any comet in recent memory. Predictions based on this explosive surge in activity became increasingly bold. It was on a trajectory that would bring it well inside the orbit of Mercury, exposing it to the full, ferocious blast of the sun's radiation. Astronomers projected that by May, it could become brilliantly visible to the naked eye. Some whispered it might even rival the planet Venus in the twilight sky, perhaps even becoming visible in broad daylight. The world, then grappling with the onset of a global pandemic, looked up with a collective sense of hope and anticipation. Here was a cosmic distraction, a celestial reassurance that the grand clockwork universe was still unfolding in all its glory, oblivious to the turmoil on our small blue world. It was to be the comet of a generation. But the universe is rarely so simple. It is a place of profound complexity, where our neat predictions often shatter against the rocks of an uncooperative reality. And as astronomers tracked Atlas with ever-increasing precision, they began to notice something unsettling. Something was wrong. The comet was not quite where it was supposed to be. To understand the gravity of this discrepancy, we must first appreciate the sublime precision of celestial mechanics. For centuries, since the time of Johannes Kepler and Isaac Newton, we have understood the fundamental laws that govern the motion of planets and comets. Gravity is the great conductor of this cosmic orchestra, its influence calculable with astonishing accuracy. We can predict eclipses to the second, centuries in advance. We can send robotic probes on decade-long journeys across billions of kilometers to rendezvous with distant worlds, arriving at a precise time and place. Our models account for the gravitational pull of the Sun, of every planet, and even the largest asteroids. The cosmic dance is intricate, but we know the steps. Imagine the solar system as a vast, flexible rubber sheet, stretched taut in the fabric of space-time. The Sun, in the centre, creates a deep, powerful depression. The planets, like smaller weights, create their own lesser dimples. A comet like Atlas is a tiny marble, rolled onto this sheet from a great distance. Its path is dictated by the curves and slopes it encounters. We can calculate that path, that elegant sweeping arc toward the central well, with near-perfect certainty. The orbital data for Atlas was fed into our most powerful computers, which charted its course, accounting for every gravitational nudge along the way. And yet, the comet was beginning to deviate from this exquisitely charted course. The discrepancy was minuscule at first, a matter of a few hundred kilometers over millions of kilometers travelled. But in the world of orbital mechanics, it was a glaring error. It was as if our marble, rolling across the rubber sheet, was somehow steering itself gently but deliberately off the path gravity had prescribed for it. A ghost was in the machine. The comet was moving as if it were being subjected to a subtle, persistent, non-gravitational force, a force that was not in our equations. Now astronomers are well aware of such forces. Comets are not perfect, inert marbles. They are active, chaotic bodies. As the Sun heats a comet's nucleus, the sublimating gases do not vent evenly from its surface. They erupt in powerful jets from fissures and weak points in the crust. These jets of gas and dust act like tiny, unpredictable rocket thrusters. If a strong jet happens to be pointing in the right direction, it can gently push the entire nucleus, altering its orbit over time. This phenomenon, known as outgassing, is the standard explanation for most cometary deviations. Think of a spinning, irregularly shaped block of dry ice. As it warms, jets of carbon dioxide will shoot out from random spots. These jets will cause the block to wobble, to spin faster or slower, and even to drift slightly in one direction or another. This is the accepted model of cometary behaviour. But Atlas refused to conform. The deviation in its orbit was strangely smooth. It lacked the jerky, unpredictable signature of random outgassing jets. It was a sustained, gentle acceleration, a persistent push that our models of cometary activity struggled to replicate. The push was too consistent. Too clean. The initial optimistic projections of its brightness began to falter. After its meteoric surge in late 2019 and early 2020, the brightening suddenly and inexplicably stalled. It hit a plateau, and then its light output actually began to fade. This was another profound anomaly. An active comet heading ever closer to the Sun should be getting brighter, not dimmer. The engine that was supposed to be powering its spectacular display seemed to be sputtering out, even as the mysterious force altering its trajectory continued to operate. The two phenomena, the steady orbital drift and the fading light, did not seem to correlate. The pieces of the puzzle did not fit. We were profoundly wrong about its behaviour. The majestic clockwork was running strangely. This is where the story of Comet Atlas transitions from a tale of astronomical anticipation to one of deep cosmic mystery. When our models fail, when the universe refuses to behave as we expect, we are presented with two possibilities. The first, and most likely, is that our understanding is incomplete. There is some subtle, natural phenomenon at play that we have not yet accounted for. Perhaps the way Atlas was rotating, combined with its internal structure, produced this uniquely smooth thrust. Perhaps its composition was unusual, leading to a strange outgassing behaviour. This is the path of scientific rigour, of Occam's razor. The simplest explanation is that we simply have more to learn about comets. But there is a second, more unsettling possibility. It is a fringe idea, a whisper at the edge of scientific discourse, but one that refuses to disappear entirely, especially when confronted with objects that defy easy explanation. The question, however hesitantly, must be asked. What if the force guiding the comet was not natural? What if the term guided was more literal than we could dare to imagine? Before we dismiss such a notion as mere fantasy, we must remember another recent visitor that challenged our assumptions. In 2017, the solar system was transited by 1A/Oumuamua, the first interstellar object ever detected. Oumuamua was an enigma from the start. It was small, shaped perhaps like a bizarrely elongated cigar or a flat pancake. It was dark, reddish, and showed no signs of a cometary coma or tail. It appeared to be a dry, inert rock, and yet as it departed our solar system it accelerated away from the Sun faster than gravity alone could explain. It too was being pushed by a mysterious non-gravitational force. With no observable outgassing to account for this push, some prominent scientists, including Avi Loeb of Harvard University, advanced a radical hypothesis. Could Oumuamua have been an artificial object? Perhaps a light sail, a thin sheet of material designed to be propelled by the pressure of starlight itself? Or maybe an ancient defunct alien probe, tumbling silently through the interstellar void? The hypothesis was and remains highly controversial. Most of the scientific community favours a natural explanation, such as the outgassing of hydrogen ice, which would be invisible to our telescopes. But the debate cracked open a door, allowing for the sober consideration of possibilities once relegated to the realm of science fiction. And now here was Atlas. Like Oumuamua, it was exhibiting a smooth, sustained acceleration that was difficult to reconcile with standard models. Unlike Oumuamua, it was clearly a comet with a visible coma, but its behaviour was no less peculiar. Could the engine driving Atlas be something other than sublimating ice? Let us engage in a thought experiment. Imagine an ancient technological civilization millions of years old. If they were to send probes to explore the galaxy, how might they do it? A metallic ship like the ones in our stories would be a conspicuous advertisement of its artificial nature. Over cosmic timescales, it would be eroded by interstellar dust and radiation. A far more clever, more patient approach would be to build your probe inside a natural object. To hollow out an asteroid, or more ingeniously, to embed a sophisticated engine and guidance system deep within the frozen heart of a comet. Such a probe would be perfectly camouflaged. It would be shielded from radiation and impacts by kilometers of ice and rock. It could use the comet's own volatile materials as a source of propellant, creating a natural-looking coma and tail as a byproduct of its propulsion system. It would be, for all intents and purposes, indistinguishable from a normal comet, except, perhaps, for a few subtle anomalies. A strange consistency in its thrust, an orbital path that was just a little too perfect, a little too clean, a trajectory that seemed less like a fall and more like a controlled descent. Is this what we were seeing with Atlas? Was its gentle, persistent push the result of a low-thrust, hyper-efficient engine, operational after millennia of silent travel? Was its destination not a random perihelion passage, but a specific observation point within our solar system? The thought is staggering in its implications. It suggests a universe not just filled with lifeless rocks and gas, but potentially populated by a patient, subtle, and unimaginably ancient intelligence. An intelligence that does not announce itself with radio signals and grand fleets, but with whispers, with ghost-like messengers disguised as the most common of celestial objects. The trajectory of Atlas was taking it high above the ecliptic plane, the flat disk where all the planets orbit. From this vantage point, it would have a perfect, unobstructed view of the entire solar system laid out before it. Was this a coincidence of its 4,000-year-old orbit, or was it a deliberately chosen flight path, the optimal route for a reconnaissance mission? The questions were as fascinating as they were unprovable. Science demands evidence, and there was nothing to suggest technology beyond the subtle wrongness of its motion. The mystery of Atlas was deepening with every passing day. The comet of a generation had become the enigma of a generation. And then, in an instant of cosmic violence, the enigma transformed. In early April of 2020, as the world watched and waited, amateur astronomers began to report a disturbing change in the comet's appearance. Its central core, the bright point of light within the hazy coma, appeared to be elongating. It looked less like a star and more like a fuzzy line. Professional observatories quickly turned their powerful eyes toward the comet, and what they saw confirmed the worst fears for its survival. The nucleus was breaking apart. The Hubble Space Telescope was commanded to observe the unfolding drama. Its crystalline vision cut through the glowing gas and dust and revealed a scene of shocking celestial destruction. The single heart of Comet Atlas was gone. In its place was a string of smaller, icy fragments, a celestial string of pearls, each piece a miniature comet in its own right, drifting apart as they continued their shared, ghostly journey toward the sun. Over the following days, the disintegration accelerated. Hubble's follow-up observations showed dozens of distinct pieces, some as large as a house, all shrouded in a shared veil of sun-driven debris. The great comet was no more. It had become a funeral procession. A diamond had shattered on the anvil of the sun. The spectacle that had been promised for May would never materialize. Instead of a single, brilliant beacon in our sky, there was now only a diffuse fading cloud of cosmic wreckage. The dream of a great comet was over. For those who had pinned their hopes on a dazzling display, it was a disappointment. But for the scientists, the death of Atlas was a treasure trove of data. It provided a rare, unprecedented look into the final moments of a comet's life. The fragmentation explained everything, and at the same time, nothing. The stalling brightness was a prelude to its demise. The comet was not just sputtering, it was crumbling from the inside out. The final act of disintegration was likely caused by the sun's warmth. The ices that held the nucleus together turned to gas, creating internal pressures and stresses that the fragile, porous structure could no longer withstand. It was, by all appearances, a completely natural death. But what of the anomalous trajectory? What of the smooth, persistent push that had sparked such wild speculation? The conventional explanation is that the fragmentation process itself was responsible. As the comet began to break up, perhaps it exposed new, large areas of ice to sunlight, creating a more stable, broad-based outgassing that mimicked the signature of a controlled thrust. The gentle push was not the sign of a hidden engine, but rather the comet's dying breath, a long, slow exhalation before it fell to pieces. This is the most plausible scientific conclusion. It wraps up the mystery in a neat, tidy, and entirely natural package. And yet, the ghost in the machine lingers. If we allow ourselves to return to our thought experiment, the disintegration of Atlas opens up an even more bizarre line of inquiry. If it were a probe, why would it self-destruct? Perhaps this was not a failure, but the fulfillment of its mission. Perhaps the primary vehicle was merely a transport system. The act of fragmentation could have been a deliberate deployment, releasing dozens of smaller targeted probes into the inner solar system. A cosmic buckshot scattering its payload throughout the terrestrial zone. Or maybe its mission complete, it executed a self-destruct sequence, a final protocol to ensure its advanced technology would not fall into the hands of a nascent, Type 0 civilization like our own. A final act of leaving no trace. These are, of course, the wildest shores of speculation. There is not a shred of direct evidence to support them. But the story of Comet Atlas serves as a profound and vital lesson in cosmic humility. It reminds us that our understanding of the universe is a work in progress. These icy visitors from the deep dark are not the simple, predictable snowballs we once imagined them to be. They are complex, dynamic worlds unto themselves, each with its own unique history and character. Some are strong and resilient, surviving dozens of fiery passes around the sun. Others, like Atlas, are cosmic weaklings, fragile agglomerations of ice and dust that cannot survive their first real encounter with the furnace of the inner solar system. This fragility is not a failure, it is a crucial data point. It informs us about the conditions under which these objects formed 4.5 billion years ago in the swirling protoplanetary disk. The ghost of Comet Atlas continues on its path. Its constituent dust and ice fragments have spread out, now an invisible river of debris tracing the orbit of the object that once was. In about 4,000 years, What remains of it will once again reach the apex of its journey, a lonely turning point in the frigid abyss far beyond the orbit of Neptune, and then it will begin the long fall back toward the Sun. Will any of it survive to complete that journey, or will its remnants have dispersed so completely that its return will be nothing more than a few faint meteors burning up in the atmospheres of the outer planets? We will not be here to know. What we do know is that the cosmos is under no obligation to meet our expectations. It is wilder, stranger, and more surprising than we can possibly imagine. Every time we point our telescopes to the sky, we are challenging our own assumptions. Comet Atlas promised a spectacle and delivered a mystery. It tantalized us with the behavior of something seemingly guided and controlled, only to disintegrate in an act of chaotic, natural violence. Or did it? The final truth of its anomalous journey may be lost forever, scattered to the solar winds along with its dusty remains. But it has left us with a gift more valuable than any celestial light show. It has left us with questions. It has forced us to confront the limits of our knowledge and to wonder once again about the true nature of the visitors that emerge, from time to time, from the endless silent dark. The watch continues. The sky is not empty, and we can be certain that another messenger is already on its way, carrying its own set of promises and its own deep secrets from the void. A single grain of sand rests between the thumb and the forefinger, a minute fragment of silicate ground down by eons of tidal friction and the patient weight of the sea. To the nerve endings in the skin, it is a microscopic burden, an insignificance so light it could be surrendered to a stray breath of wind without a second thought. It is a relic of a planetary past, a tiny solid in a world of vast oceans. Yet, when this solitary speck is raised toward the midnight sky and held at the full length of an outstretched arm, the geometry of the cosmos undergoes a staggering transformation. That grain of sand, small enough to be lost in the whirls of a fingerprint, now serves as a shutter across a window into the infinite. Behind its jagged edges, hidden from view by a few milligrams of mineral, lie 10,000 entire galaxies. Each of those 10,000 islands of light contains hundreds of billions of suns. Within that narrow corridor of space, obscured by a single grain of earthly grit, the history of the universe is stacked in layers of light and time. Trillions of worlds, countless stellar nurseries, and the wreckage of ancient supernovae all occupy that tiny patch of perceived darkness. For decades, this deep field was thought to be a well-understood tapestry, a predictable progression of cosmic growth. But a new sentinel, the III Atlas project, dedicated to the study of ionization, ignition, and interaction, has turned its gaze toward that specific void and found something that defies the established order of the heavens. Deep within the data streams of the III Atlas, a signal has emerged from the silence. It is not the steady burn of a modern star or the familiar swirl of a mature galaxy. Instead, it is a flickering ghost, a spectroscopic stutter that has travelled across the expanding throat of the universe for nearly 13.8 billion years. This light began its journey when the cosmos was a mere 180 million years old. At this distance, we have reached the frontier of redshift 20, a realm where the very fabric of space-time has been stretched so severely that the physics of the local universe begins to fracture and dissolve. To understand the magnitude of this discovery is to understand the nature of light as a messenger. As the universe expands, it pulls at the waves of radiation travelling through it, elongating them like golden threads caught in a widening loom. By the time the light from this ancient era reaches our senses, it has been stretched by a factor of 21. The ultraviolet screams of the first celestial objects have been hushed, pulled down into the long invisible wavelengths of the deep mid-infrared. At redshift 20, we are no longer looking at the universe as it is, or even as it was in its middle age. We are looking at the very moment the first candles were lit in a house that had been cold and dark for an eternity. This era, known as the Dawn of Light, represents the most significant transition in the history of existence. Before this moment, the universe was a featureless, opaque ocean of neutral hydrogen gas, a thick, suffocating fog that trapped all radiation in a perpetual night. There were no stars, no galaxies, and no heavy elements. there was only the slow, invisible pull of gravity acting upon vast clouds of primordial mist. The signal identified by the Triple I Atlas is the first evidence of the path, the specific, violent trajectory by which the cosmos tore itself out of this dark age. At the boundary of redshift 20, the mathematical blueprints we use to describe the formation of suns begin to fail. The standard models of stellar evolution suggest that structure should emerge slowly, with small clumps of gas gradually coalescing over hundreds of millions of years. However, the data from the Triple I Atlas reveals a reality that is far more aggressive. The signals coming from the 180 million year mark suggest the presence of objects far too massive and far too bright for their age. It is as if the universe, in its infancy, found a shortcut, a way to bypass the slow crawl of traditional physics to ignite the first fires of creation with a ferocity that challenges our understanding of gravity itself. The path is the bridge between that primordial soup and the complex, structured reality that eventually gave rise to the heavy elements found in our own bodies. Every atom of carbon in the human heart and every spark of oxygen in the lungs was forged in the heat of a star, but those stars could not exist until the first generation of giants cleared the way. The Triple I Atlas has captured the exact moment this clearing began. It is the record of a synchronized phase transition, a cosmic ignition that occurred across the vastness of space with a precision that seems almost calculated. Looking into this data is not merely an act of astronomical observation, it is an act of ancestral recovery. We are tracing the lineage of light back to its absolute origin. The flickering ghost at redshift 20 is the first heartbeat of the macrocosm. It represents the shattering of the Dark Ages and the beginning of the era of interaction where matter and light finally began the long, complex dance that would result in the world we see today. As the Triple I Atlas continues to peel back the layers of the deep field, we find that the grain of sand held against the sky is not just obscuring 10,000 galaxies, it is obscuring the very blueprint of our existence, a map written in stretched light and ancient radiation, waiting to be decoded by the species that the universe eventually grew to observe itself. The physics of the old world are falling away, replaced by the terrifying and beautiful reality of a beginning that was far more explosive and structured than we ever dared to believe. To grasp the nature of the redshift frontier, one must perceive space not as a hollow vacuum, but as a living, stretching fabric. As the universe expands, it does not merely push galaxies apart, it distends the very geometry of the void between them. Every kilometre of emptiness is subject to a relentless intrinsic growth. When a photon of light is emitted from a primordial source, it begins its journey as a tight, energetic coil of radiation. If that source exists at the boundary of redshift 20, that light must traverse a chasm of time so vast that the space it occupies expands significantly during its transit. By the time this light reaches the inner solar system, the waves have been pulled apart, flattened and elongated until they no longer resemble their original form. In the local universe, the most energetic stars announce their presence through the piercing brilliance of ultraviolet rays. These are short, high-frequency waves that carry the signature of extreme heat and violent nuclear fusion. However, for the light originating at redshift 20, the expansion of the cosmos has acted as a titanic cosmic bellows. The waves have been stretched by a factor of 21. This means that a photon, which began its life as a sharp, invisible ultraviolet pulse, has been transformed into a long, languid wave of deep mid-infrared radiation. It has moved entirely out of the realm of human vision, and even beyond the reach of standard optical telescopes. It has become a ghostly heat, a thermal whisper from the dawn of time that can only be detected by instruments capable of operating in the profound cold of deep space. This is the specific domain of the James Webb Space Telescope, a sentinel of gold and beryllium stationed at the second Lagrange point, 1.5 million kilometers away from the heat of the Earth. Its primary mirror, composed of 18 hexagonal segments spanning 6.5 meters, acts as a massive collector for these stretched infrared threads. But the telescope is merely the eye. The Triple Y Atlas is the mind that directs its gaze. This project, the Ionization, Ignition and Interaction Atlas, is designed to map the precise moment when the first light-producing objects fractured the primordial darkness. it focuses its immense sensitivity on the boundary of redshift 20, a region of the cosmic timeline that was, until very recently, considered a total observational void. At this distance, the visible universe begins to undergo a fundamental phase change. We are looking back to a period when the cosmos was only 180 million years old, a mere fraction of its current age of 13.8 billion years. In this era, the universe was transitioning from a state of total neutrality to one of ionization. The Triple-I Atlas seeks the very first bubbles of light that formed in the darkness, pockets of ionized gas created by the radiation of the earliest stars and black holes. These bubbles represent the ignition in the project's name, the spark that ended the cosmic dark ages. The physics at redshift 20 are characterized by a sense of fracture because they challenge the chronological limits of the known universe. At this frontier, we observe a strange paradox of scale and speed. The light captured by the Triple-I Atlas suggests that structure was forming far more rapidly than any computer simulation of the early universe had predicted. According to the standard laws of cold dark matter, it should take hundreds of millions of years for gravity to pull enough gas together to ignite a star. Yet, at redshift 20, we see signals of massive, luminous entities already in existence. The path identified by the researchers indicates that the early universe possessed a hidden efficiency, a way of condensing matter into light that bypasses our current understanding of cosmic gestation. As we probe deeper into this infrared frontier, the very concept of a galaxy begins to break down. We are not seeing the majestic spirals or giant ellipticals of the modern era. Instead, the Triple-I Atlas reveals irregular hyperluminous knots of activity. These are the first interactions, the interaction phase of the mission, where the first stars and the first black holes began to influence the gas around them. This interaction created a feedback loop of radiation that began to strip electrons from the surrounding hydrogen atoms, a process that would eventually render the entire universe transparent. The redshift frontier is therefore more than just a distance, it is a wall of time. Beyond redshift 20, the universe is a wall of opaque mist impenetrable to light. To look at this boundary is to stand on the edge of a great cliff and peer down into the very foundations of reality. The Triple-I Atlas is documenting the first moments of the Great Awakening, catching the very first photons that managed to escape the primordial fog. These infrared signals are the oldest messengers in existence, carrying the blueprints of a universe that was just beginning to learn how to shine. Each photon is a survivor of a journey across 13.6 billion years of expanding space, arriving at our detectors as a faint red-shifted testimony to the violent and sudden birth of the light-filled world we now inhabit. Before the first fires of creation could be struck, the universe existed in a state of profound and absolute equilibrium. This was the era of the cosmic dark ages, a period of several hundred million years where the macrocosm was little more than a vast unlit ocean of neutral hydrogen. Following the initial cooling of the afterglow from the Big Bang, the cosmos had entered a phase of total invisibility. There were no suns to illuminate the void, no galaxies to anchor the horizon, and no heavy elements to form the solid ground of a planet. Instead, the entire expanse of space-time was filled with a featureless soup of primordial gas, mostly hydrogen with a small fraction of helium, distributed with a terrifyingly smooth uniformity. This era was not a vacuum of activity, but rather a silent cosmic pressure cooker. While the visible spectrum remained black, a hidden architecture was already being assembled in the shadows. Dark matter, the invisible and mysterious substance that outweighs ordinary matter by a factor of 5 to 1, acted as the primary architect of this period. Because dark matter does not interact with light, it was unaffected by the radiation pressure that had kept ordinary gas dispersed in the earliest moments of existence. It began to clump together under the influence of its own gravity, forming a complex three-dimensional web of filaments and nodes. These dark matter halos served as gravitational traps, pulling the neutral hydrogen gas into their depths. Within these invisible wells, the density of the gas began to rise. It was a slow, agonizingly patient process. The hydrogen atoms drifted into the centers of the dark matter concentrations, colliding and losing energy, gradually sinking deeper into the gravitational pits. To an observer, if one could have existed in that era, the universe would have appeared as a cold and silent wasteland. There was no heat, no movement beyond the sluggish drift of gas, and no sound. Yet beneath this surface of stillness, the internal pressure of these gas clouds was mounting. The universe was holding its breath, waiting for the density and temperature at the hearts of these clouds to reach a critical threshold. This transition from the featureless chaos of the Dark Ages to the structured brilliance of the first stars is what researchers call the path. It is far more than a simple chronological sequence. It is a rigorous mathematical blueprint that guided the evolution of the entire cosmos. The path represents the set of physical laws, the fine-tuned constants of gravity, nuclear forces, and thermodynamics that dictated how a universe made of nothing but gas and dark matter could eventually produce the complexity of biological life. It is the fundamental logic of reality, a series of inevitable steps where gravity overcomes entropy, and where the simple becomes the complex through the sheer weight of time. The path was etched into the very fabric of the universe during the first microsecond of existence, but it only became manifest during the Dark Ages. It was the blueprint that determined the mass of the first stars, the rate at which galaxies would assemble, and the specific sequence of nuclear reactions that would one day forge the carbon in a human ribcage. Without this mathematical guidance, the gas of the Dark Ages would have remained a sterile mist forever. Instead, the path ensured that the neutral hydrogen would eventually ignite, transforming the cold pressure cooker of the early universe into a laboratory for the creation of matter. As the tens of millions of years stretched into hundreds of millions, the dark matter scaffolding grew more pronounced. The filaments of the cosmic web thickened, and the nodes where they intersected became the sites of intense gravitational activity. In these locations, the neutral hydrogen was no longer a diffuse soup. It had become a series of dense protostellar clouds. The silence of the Dark Ages was nearing its end. The pressure at the core of the most massive cloud was approaching the point where the electrostatic repulsion between hydrogen nuclei would finally be overcome by the crushing force of gravity. This period of darkness was a necessary gestation. It allowed the universe to cool and the large-scale structure of the cosmos to settle into the patterns that would define the next 13 billion years. The Dark Ages were the final era of cosmic simplicity. Once the first star ignited, the universe would be forever changed, polluted by light and heavy elements, and set upon a trajectory of increasing complexity. The path was the invisible hand that steered the cosmos through this lightless wilderness, ensuring that the primordial chaos would not be the end of the story, but merely the prologue to a structured reality capable of supporting the existence of a mind. The III Atlas project, by looking back to Redshift 20, is essentially attempting to read the first pages of this blueprint, capturing the exact moment when the mathematical potential of the path was translated into the physical reality of the first light. The transition from the absolute stillness of the Dark Ages to the era of the first stars is not marked by a gentle illumination, but by a violent struggle between nascent radiation and a primeval fog. This fog, composed of neutral hydrogen atoms, acts as a cosmic gatekeeper. Each atom consists of a single proton orbited by a single electron, and this simple configuration possesses a specific and ravenous appetite for energy. When the first stars ignited, they began to flood the void with high-energy ultraviolet photons. However, for a photon to travel through the early universe, it had to navigate a minefield of neutral hydrogen. If a photon possessed a wavelength of exactly 121.6 nanometers, the precise energy required to kick a hydrogen electron from its ground state to its first excited state, it was instantly absorbed. This specific interaction is known as the Lyman alpha transition, and in the early universe it created a literal wall for light. In the spectroscopic data captured by our most advanced instruments, this physical barrier manifests as a sharp vertical plunge in the intensity of light, a phenomenon researchers call the Lyman alpha break. Below this specific wavelength, the universe is effectively opaque. Every photon shorter than this limit is swallowed by the neutral gas, leaving behind a void in the data. To an observer, a galaxy from this era does not appear as a continuous rainbow of colours. Instead, it looks as if it has been severed by a guillotine. the spectrum proceeds normally through the long red wavelengths, only to vanish into total darkness at the exact point where the neutral hydrogen begins its feast. This cliff in the data is the signature of the early universe, a fingerprint of a time when the cosmos was still struggling to become transparent. The challenge for teams like the Cosmic Evolution Early Release Science Project is that the expansion of the universe has shifted this cliff far beyond its original position. Because these galaxies are moving away from us at incredible velocities, the light they emit is stretched. By the time the light from a galaxy at redshift 20 reaches the hexagonal mirrors of the James Webb Space Telescope, the Lyman alpha break has been pushed from the ultraviolet range deep into the mid-infrared. To find these ancient structures, astronomers employ a technique known as the dropout method. They observe the same patch of sky through a series of different filters, each sensitive to a specific slice of the infrared spectrum. The dropout method is a masterwork of deductive reasoning. If a candidate galaxy is visible in a filter that captures very long infrared waves, but completely disappears in a filter that captures slightly shorter waves, researchers know they have found the Lyman alpha break. The galaxy has dropped out of the shorter wavelength filter because the neutral hydrogen surrounding it has absorbed all the light at those frequencies. At redshift 20, the light has been stretched by a factor of 21, meaning the galaxy will be invisible in almost every standard filter, appearing only in the deepest, reddest channels available to our technology. This disappearance is not a failure of the equipment. It is the most reliable evidence we have of an object's extreme distance and antiquity. The Cosmic Evolution Early Release Science team, working in tandem with the III Atlas project, uses these dropouts to map the large-scale structure of the infant universe. They are not merely looking for individual stars, but for the first massive clusters of matter that manage to punch holes in the neutral hydrogen fog. Each dropout represents a flickering candle in the dark, a localized region where the first generations of stars were beginning to ionize the gas around them. By cataloging these cliffs in the data, scientists can trace the progress of reionization, watching as the bubbles of clear space grew and eventually merged to create the transparent cosmos we inhabit today. This technical hunt requires a precision that borders on the miraculous. The signals are incredibly faint, often consisting of only a few dozen photons hitting the telescope's detectors every hour. To distinguish a true high redshift dropout from a piece of local dust, or a much closer, cooler star, the III Atlas project must perform rigorous checks on the mathematical shape of the light curve. A true Lyman alpha break is unmistakable in its sharpness. It is a sudden, total extinction of light that no other physical process can replicate. When such a signal is confirmed at redshift 20, it tells us that we are looking at a structure that existed when the universe was less than 2% of its current age. The data cliffs identified by these projects are the primary evidence for the path. They show that the first galaxies were not isolated accidents, but part of a synchronized awakening. The dropout method has revealed that these early structures were far more numerous and far more luminous than our previous theories had allowed. We are seeing a universe that was in a hurry to ignite. The Lyman alpha break, once a barrier to our understanding, has become our most powerful tool for measuring the depth of time. It allows us to pinpoint the exact moment when the neutral hydrogen wall began to crumble under the sustained assault of the first stellar radiation, marking the end of the Dark Ages and the beginning of the long, light-filled journey toward the present. The findings of the III Atlas project have moved beyond the realm of mere discovery and into the territory of a foundational crisis for modern cosmology. While the dropout method was expected to reveal small, fragile clumps of stars, the tentative first steps of a universe finding its feet, the data cliffs returning from the redshift 20 boundary tell a far more aggressive story. In the specific coordinates where the project focused its deepest gaze, it did not find the expected cosmic toddlers. Instead, it identified a cluster of galaxies so massive, so luminous, and so structurally mature that they should not, by any established rule of physics, exist so early in the timeline of the universe. These anomalies appear as jagged spectroscopic scars across the mid-infrared data. According to the standard model of cosmic evolution, the lambda cold dark matter model, the assembly of large-scale structures is a slow, hierarchical process. In this bottom-up scenario, gravity takes hundreds of millions of years to pull small clouds of gas together into tiny dwarf-like galaxies, which then slowly merge over billions of years to form the titanic spirals and ellipticals we see in the local universe. At 180 million years after the beginning, the universe should have been a landscape of small-scale chaos. Yet, the Triple-I Atlas has captured the light of stellar metropolises that contain the mass of tens of billions of suns. Finding these structures at redshift 20 is equivalent to walking into a prehistoric forest and finding a fully realised skyscraper standing among the saplings. The presence of these massive galaxies suggests that the early universe was far more efficient at building structure than our most sophisticated computer simulations ever predicted. In the Standard Model, the conversion of primordial gas into stars is a self-regulating and relatively inefficient process. As the first stars ignite, their intense radiation and stellar winds push away the surrounding gas, starving the galaxy of the fuel it needs to grow larger. This feedback is supposed to act as a cosmic brake, preventing galaxies from becoming too massive too quickly. The Triple-I Atlas data suggests that at redshift 20, this brake was either absent or entirely overwhelmed by a gravitational deluge. The efficiency of this primordial forge is staggering. To reach the masses indicated by the data cliffs, these galaxies must have been converting gas into stars at a rate hundreds of times faster than anything observed in the modern era. We see evidence of a hyper-accelerated cosmic metabolism, where the cold dark matter halos acted not as passive containers, but as high-pressure funnels that drove gas into the centres of these structures with relentless force. This was not a slow accretion, it was a violent wholesale collapse of matter into light. The path revealed here is one of extreme urgency, a universe that refused to wait for the slow passage of eons to begin its work of complexification. This discovery has sent a shockwave through the scientific community as it threatens to shatter the house of glass that is our current understanding of the early cosmos. If the lambda cold dark matter model cannot account for the existence of these behemoths, then the very foundations of our cosmological constants may need to be revised. It raises the possibility that our measurements of the strength of gravity in the early universe, or our understanding of the nature of dark matter itself, are fundamentally incomplete. The Triple-I Atlas has pulled back the curtain on a reality where the rules of the game were different, where the dark matter scaffolding was denser, the gas was more responsive, and the first light was far more powerful than we had dared to conceive. The cluster of data cliffs indicates that these massive galaxies are not isolated flukes or statistical outliers. They are part of a synchronized population, a generation of monsters that dominated the landscape of redshift 20. Their light, stretched and hued by the expansion of space, carries the signature of a universe that was already in full bloom while we expected it to be in its infancy. This efficiency of structure building has profound implications for everything that followed. These massive galaxies would have been the primary drivers of reionization, their collective radiation carving out immense bubbles in the neutral hydrogen fog far faster than smaller, more isolated stars could have managed. We are forced to confront the idea that the path from chaos to structure was a shortcut. The Triple-I Atlas has revealed a universe that possessed an innate, almost predatory drive toward complexity. The dark matter and gas did not merely drift. They conspired to create these massive anchors of light at the earliest possible moment. As the project continues to refine its map of these anomalies, the Standard Model of cosmic evolution sits on a precipice. The infrared photons hitting our detectors are the evidence of a prehistoric reality that was far more energetic, far more crowded, and far more efficient than our theories allowed. We are looking at a forge of such intensity that it bypasses the need for the slow crawl of time, creating a universe of giants in the very heart of the dark. Within the deepest pits of the dark matter halos, the first true structures began to take shape, emerging not as the modest, long-lived stars we observe in the night sky today, but as the population 3 monsters, the primordial giants of the first dawn. In the modern universe, star formation is a process of fragmentation and restraint. When a cloud of gas collapses in the present era, it is filled with the dust of previous generations, elements like carbon, oxygen, and iron. These heavy elements, which astronomers call metals, act as cosmic refrigerants. They allow the gas to shed its heat through infrared radiation, causing the cloud to break into thousands of small sun-sized pieces. But in the era of redshift 20, the universe was a place of absolute unadulterated purity. There was no dust, no metal, and no cooling agents. There was only the raw primordial mix of hydrogen and helium. Because these light gases are notoriously poor at shedding heat, the primordial clouds could not fragment into small pieces. Instead, they remained as singular, colossal masses of gas, swelling and churning under the mounting weight of their own gravity. To reach the threshold of nuclear ignition, these clouds had to grow to gargantuan proportions, far exceeding the limits of any star forming in the modern Milky Way. The result was a generation of behemoths, stars that reached 300 times the mass of our Sun. These were the first light bringers, celestial leviathans that stood as the only points of brilliance in a dark eternity. The appearance of these stars was a radical departure from the aesthetic of the modern cosmos. They did not burn with the steady yellow warmth of our Sun or the deep red of a cooling dwarf. Instead, they were searing, violet-white furnaces of ultraviolet radiation. Their surfaces were so hot that they emitted light primarily in the shortest, most energetic wavelengths. This hard, ionizing radiation began to scream into the void, striking the surrounding neutral hydrogen with the force of a cosmic hammer. This was the moment the path transitioned from a theoretical blueprint into a physical reality of fire and light. These firstborn giants were the ultimate paradox of the early universe. They were the most powerful objects in existence, yet they were destined for the briefest of lives. While a star like our Sun can husband its hydrogen fuel for 10 billion years, a population 3 monster lived at a suicidal pace. The crushing gravity at their cores forced nuclear fusion to occur with a ferocity that exhausted their entire fuel supply in a mere 3 million years, a blink of an eye in cosmic terms. They were the ephemeral architects of the universe, existing just long enough to fundamentally alter the chemistry of space before vanishing into the dark. The contrast between these primordial giants and the stars of today is the difference between a singular world-altering explosion and a steady, controlled burn. Modern stars are polluted by the wreckage of the past, their chemistry a complex tapestry of every supernova that came before them. But the population 3 stars were the progenitors, the original source of all complexity. Within their hyper-pressurized cores, the very first atoms of carbon, oxygen, and silicon were forged from the fusion of hydrogen and helium. They were the first alchemists turning the simple gas of the Big Bang into the building blocks of planets and life. When the life of a population 3 giant reached its inevitable conclusion, it did not go quietly. Because of their immense mass, many of these stars ended their lives in pair instability supernovae. This is a type of explosion so total and so violent that it defies the standard rules of stellar death. In a typical supernova, the core of a star collapses into a neutron star or a black hole, while the outer layers are blown away. But in a pair instability event, the entire star is consumed. The internal radiation pressure drops so suddenly that the star collapses and then ignites its entire mass of oxygen and silicon in a single terminal heartbeat. The resulting explosion leaves nothing behind. No black hole, no remnant, only a vast expanding cloud of heavy elements seeded into the pristine vacuum. These monsters were a necessary bridge. Their intense ultraviolet light began the process of rionization, carving out the first bubbles of transparency in the cosmic fog. Their deaths provided the metals that would allow the next generation of stars to be smaller, more stable, and more numerous. The III Atlas project, by detecting the signatures of these giants at redshift 20, is witnessing the era of the first light bringers, a time when the universe was populated by short-lived gods of fire that sacrificed themselves to ensure the cosmos would never be dark again. We are seeing the beginning of the end of the Dark Ages, as the first generation of stars tore the veil of neutral hydrogen asunder and began the long process of transforming the universe from a sterile soup into a laboratory of infinite possibility. The era of the first stars did not merely introduce light into the darkness, it initiated a violent and fundamental transformation of the cosmic medium itself. For hundreds of millions of years, the universe had been an opaque reservoir of neutral hydrogen, a gas that acted as a universal sponge for radiation. Any photon of sufficient energy was immediately seized by a hydrogen atom. Its journey terminated before it could even leave its neighbourhood. But as the population 3 giants ignited in their thousands and then their millions, they began to wage a relentless war against this primordial fog. This was the onset of reionization, a synchronized phase transition that would eventually strip the universe of its neutrality and grant it the gift of transparency. The mechanism of this change was a process of atomic demolition. Each of the massive first stars was a powerhouse of ionizing radiation, flooding the surrounding space with high-energy ultraviolet photons. When such a photon struck a neutral hydrogen atom, it did not merely nudge it. It delivered a blow so energetic that the atom's lone electron was violently torn from the grip of its central proton. The atom, once a stable and light-absorbing entity, was shattered into its constituent charged particles. This was the birth of a plasma, a sea of free-roaming electrons and protons that, unlike neutral gas, allowed high-energy light to pass through relatively unhindered. Around every primordial star and every nascent galaxy, a bubble of clarity began to grow. These were spheres of ionized hydrogen, expanding outward like ripples in a dark pond. Within these bubbles, light could travel for thousands, then millions of light years without being swallowed. But the edges of these bubbles were battlefronts. At the boundary, the intense radiation of the stars met the cold, indifferent wall of the neutral dark ages. For a time, the universe was a Swiss cheese of light and shadow, isolated pockets of brilliance separated by vast, light-choking curtains of primordial mist. The data from the III Atlas project reveals that this was not a slow or hesitant process. Instead, it was a synchronized awakening that occurred with terrifying speed. As the first galaxies grew more massive and the population 3 stars were joined by the first supermassive black holes, the production of ionizing photons reached a tipping point. The bubbles of clarity began to expand at a significant fraction of the speed of light. They grew until they touched, their boundaries overlapping and merging in a cosmic chain reaction. This was the moment of the Great Clearing, a transition as sudden and profound as the melting of a world-spanning glacier. This phase transition was a moment of cosmic clarity. Before ionization, the universe was a wall. After ionization, it became a window. The fog that had defined the first few 100 million years was burned away, leaving behind a diffuse ionized plasma that was almost entirely transparent to radiation. For the first time since the cooling of the Big Bang, a photon emitted on one side of the cosmos could travel across the entire expanse of space-time to be captured by a telescope billions of years in the future. The universe had effectively opened its eyes, allowing the light of the distant past to finally reach the eyes of the present. This clearing was not merely a change in visibility, it was a permanent alteration of the cosmic environment. The heat injected into the gas during reionization raised the temperature of the intergalactic medium to tens of thousands of degrees. This heat acted as a new form of pressure, preventing smaller clumps of gas from collapsing into stars and thereby regulating the growth of future galaxies. The path had led the universe through a violent forge, using the radiation of the firstborn monsters to sterilize the vacuum and set the stage for a more orderly, long-term evolution. The III Atlas project captures the signatures of this transition by looking at the way light from distant quasars is filtered through the remaining patches of neutral gas. As we peer back toward redshift 20, we see the final remnants of the cosmic fog being shredded by the first light. We see a landscape of beautiful, violent change, where the very atoms of the universe were being broken apart to make way for the light. This was the true beginning of the history of the stars, the moment the universe transitioned from a cold, silent pressure cooker into a vast, transparent theatre where the drama of cosmic evolution could finally be seen. The light that reached us across 13 billion years is the survivor of this war, a testimony to the era when the cosmos first learned to let the light through, turning an opaque mist into a transparent expanse that stretches to the very edge of time. While the light of the first stars provides a visual record of the early universe, it is merely the foam on the crest of a much deeper, invisible tide. Beneath the brilliance of the population 3 giants and the glowing bubbles of Orionization lies a hidden architecture that dictates the movement of all visible matter. This is the invisible scaffolding of the cosmos, a vast network of dark matter that preceded the light and provided the foundation upon which the first galaxies were built. To see this structure, researchers cannot rely on traditional telescopes that capture photons. Instead, they must observe the way the universe itself is bent and distorted by an unseen weight. The primary tool for this investigation is gravitational lensing, a phenomenon where the very fabric of space-time acts as a cosmic magnifying glass. According to the laws of general relativity, a massive concentration of matter does not simply exist within the void, it curves the geometry of the vacuum. When the light from a distant ancient source travels toward the Earth, it must navigate these curves. If it passes through a region dominated by a massive halo of dark matter, its path is diverted. The light is stretched, amplified, and occasionally split into multiple images or glowing arcs. By meticulously analysing these distortions, the III Atlas project can calculate the exact mass and distribution of the invisible substance that caused the bending. The data returning from the redshift 20 boundary has revealed a startling discrepancy between theory and reality. The halos of dark matter identified in the early universe are significantly denser and more compact than any current computer simulation had predicted. In the standard model of cosmic growth, dark matter should have formed broad, diffuse wells that slowly deepened over hundreds of millions of years. However, the III Atlas has found gravitational footprints that are sharp and intense. These are not shallow depressions in the fabric of space, but deep gravitational canyons. This density indicates that the dark matter scaffolding was far more robust and established at 180 million years than previously believed, providing a high-pressure environment that forced the assembly of the first structures. This invisible matter acted as the essential gravitational glue of the early cosmos. In the wake of the Big Bang, the ordinary gas of hydrogen and helium was hot and restless, possessed of enough kinetic energy to resist the relatively weak pull of its own gravity. Without an external force to bind it, the gas would have remained a thin, sterile mist, never reaching the densities required to ignite a star. Dark matter provided that force. Because it does not interact with light or radiation, it was able to begin clumping together almost immediately after the beginning of time, unaffected by the chaotic pressures that kept ordinary matter dispersed. By the era of redshift 20, these dark matter halos had grown into immense invisible traps. As the neutral hydrogen gas drifted through the dark ages, it was inexorably drawn into these gravitational wells. The gas did not merely fall, it was funneled into the centres of the halos with a relentless, focused intensity. This was the true origin of the path, the invisible corridors of dark matter that guided the primordial soup toward its destiny as a structured reality. The higher-than-expected density of these halos explains why the first galaxies discovered by the III Atlas are so massive and mature. The scaffolding was stronger than we knew, and therefore the construction of the universe could proceed at a pace that defies our earlier, more conservative estimates. The relationship between this invisible scaffolding and the first light was a complex feedback loop of interaction. The dark matter dictated where the stars would be born, but once those stars ignited and eventually died in colossal explosions, their radiation and shock waves pushed back against the gas, though the dark matter remained unmoved. This cosmic web of filaments and nodes created a map of the future. Every large-scale structure we see in the modern sky, from the Great Attractor to the local group of galaxies, is a descendant of the patterns established by these dense ancient halos. The III Atlas project has effectively turned the universe into a laboratory of shadows. By mapping the gravitational lensing at the edge of the visible horizon, scientists are uncovering the skeletal remains of the infant universe. They are seeing the path not as a series of accidents, but as a rigid mathematical necessity imposed by the distribution of dark matter. This invisible scaffolding was the silent partner in every nuclear reaction and every galactic merger. It was the architect of the Dark Ages, ensuring that when the light finally arrived, it would have a place to gather, a place to grow, and a place to eventually forge the complexity of a living world. The discovery of these hyperdense halos at redshift 20 suggests that the universe was never a disorganized chaos. It was a structured environment from the very beginning, held together by a dark gravitational embrace that we are only now beginning to measure. In the meticulous mapping of the early universe, the III Atlas project has uncovered a secondary, far more radical route within the cosmic blueprint, a shortcut in the evolution of matter that defies the traditional understanding of how the heavens were built. While the majority of primordial gas followed the arduous journey of condensing into the first generations of stars, certain sectors of the cosmos opted for a more direct and violent expression of gravity. This is the phenomenon of direct collapse, a process where the intermediate stage of stellar birth is bypassed entirely, allowing vast monolithic clouds of hydrogen to fall inward until they vanish into the singular throat of a black hole. This obvious path was born from a rare and specific set of conditions within the infant universe. In these high-density regions, massive reservoirs of neutral gas were trapped within the deep gravitational canyons of the dark matter scaffolding. Under normal circumstances, as this gas collapsed, it would have fragmented into thousands of smaller clumps, each igniting as a star. However, the III Atlas has identified evidence of a powerful environmental deterrent: the intense ultraviolet radiation from neighbouring star-forming regions. This radiation, specifically in the Lyman-Werner bands, acted as a cosmic sterilizer. It prevented the formation of molecular hydrogen, the primary coolant that allows gas clouds to break apart. Without the ability to cool and fragment, the gas remained as a single colossal entity, a mountain of matter that knew only one direction: down. As the weight of these clouds became unsustainable, the collapse was no longer a gentle accretion, but a catastrophic, inward-rushing deluge. Tens of millions of suns' worth of gas fell toward a central point at significant fractions of the speed of light. There was no nuclear fire to push back against this weight, no stellar wind to arrest the fall. In a period of time that is nearly instantaneous on a cosmic scale, the gas crossed the event horizon, surrendering its volume to become a primordial black hole of staggering proportions. These objects were not the small stellar mass remnants left behind by dying stars. They were born as giants, possessing the mass of 100,000 to 1 million suns from the very moment of their inception. This discovery provides the missing link in a mystery that has long haunted the halls of cosmology: the existence of supermassive black holes in the very early universe. Before the data from the III Atlas, scientists struggled to explain how black holes with the mass of billions of suns could exist only a few 100 million years after the beginning. If they had started as small stellar remnants, there simply would not have been enough time for them to grow to such sizes by feeding on surrounding gas. The direct collapse path solves this paradox by providing a seed that is already a titan. It is a cosmic shortcut that allowed the universe to leapfrog over millions of years of gradual growth, placing the anchors of future galaxies in the void while the first stars were still struggling to ignite. The III Atlas project detects these primordial monsters by the unique and terrifying signature of their growth. As gas falls into these direct collapse black holes, it is accelerated to nearly the speed of light, rubbing against itself and heating to millions of degrees before it is consumed. This process creates a brilliant high-energy glow known as an accretion disk, which emits a spectrum of light that is distinct from the thermal signature of a star. By observing these signals at redshift 20, researchers can see the first quasars, the glowing hearts of infant galaxies, flickering into existence. These are the beacons of the direct collapse, marking the locations where gravity achieved its most efficient victory over matter. This path represents a fundamental shift in our perception of the early universe. It suggests that the cosmos was not just a nursery for stars, but also a laboratory for the creation of extreme gravity. The direct collapse black holes were the first true masters of their environment, their immense gravitational pull acting as a secondary scaffolding that complemented the dark matter. They drew in gas and stars alike, creating the dense, high-pressure environments where the first massive galaxies could assemble. They were the engines of interaction, their radiation contributing to the rionization of the universe, and their gravity shaping the orbits of everything around them. The existence of this shortcut implies that the path was never a single narrow road. It was a multifaceted strategy for the emergence of complexity. In some places, the universe chose the slow, delicate work of stellar fusion. In others, it shows the sudden absolute power of the singularity. The Triple Biao Atlas has shown that these direct collapse giants were not rare accidents, but a foundational component of the early landscape. They were the pioneers of the deep field, the first objects to reach the scales required to anchor the massive structures we see today. By bypassing the process of star formation, the universe ensured that its most massive structures would have the gravitational foundations they needed to survive and grow across the billions of years that followed. We are looking at a universe that was as much a product of its shadows as it was of its light, built upon a foundation of primordial giants that fell into the dark so that the galaxies could one day rise. The first stars were born to be martyrs, their very existence a desperate and short-lived defiance of the dark. These population 3 giants, forged from the untainted gases of the Big Bang, possessed a chemistry that was as simple as it was unstable. Without the presence of heavy elements to regulate their internal temperatures, they were forced to accumulate immense quantities of matter, reaching hundreds of times the mass of the Sun, just to achieve the pressures necessary for nuclear ignition. This mass was their power, but it was also their death sentence. The gravity at their cores was so crushing that it drove the process of nuclear fusion at a rate that was fundamentally suicidal. They were the brightest torches in the history of the cosmos, but they were also the most ephemeral. Within the hyper-pressurized hearts of these primordial leviathans, the path achieved its most critical chemical milestone. In the modern universe, stars burn hydrogen into helium over billions of years, but in the population 3 monsters, this phase was a mere prelude. As the hydrogen was exhausted, the core temperatures soared to hundreds of millions of degrees. Under this extreme thermal duress, the helium nuclei began to fuse, a process known as the triple alpha reaction. This was the moment of the first great synthesis. For the first time in the history of existence, the simple, 2-element universe was being transformed. From the fusion of helium emerged carbon, the backbone of all known biological chemistry. Then, through the addition of another helium nucleus, oxygen was forged, the vital breath of future worlds. This nucleosynthesis was not a gentle evolution, but a frantic, high-stakes alchemical reaction. The stars were struggling to maintain an equilibrium between the outward push of radiation and the inward pull of their own immense gravity. As they forged heavier and heavier elements, neon, magnesium and silicon, they were essentially building the very things that would eventually lead to their destruction. The heavier the elements in the core, the more energy was required to prevent a total collapse. The population 3 stars were locked in a race against time, burning through their fuel supplies with a ferocity that saw entire sun-sized reservoirs of hydrogen consumed in the equivalent of a human afternoon. The end of these giants was dictated by a unique quirk of high-energy physics known as pair production. As the core temperatures reached their peak, the gamma-ray photons produced by fusion became so energetic that they began to spontaneously transform into pairs of matter and antimatter, electrons and positrons. This transformation was a catastrophe for the star. Gamma rays provide the outward pressure that holds the star up against gravity. When those rays turned into particles, that pressure vanished. In a single, terrifying moment, the star lost its internal support. The outer layers, containing the mass of hundreds of suns, began to fall inward at a significant fraction of the speed of light. The resulting collapse triggered a nuclear explosion of such total and absolute magnitude that it defies standard classification. This was a pair instability supernova. Unlike the supernovae of the modern era, which leave behind a neutron star or a black hole as a tombstone, a pair instability event is a total annihilation. The entire mass of the star, the newly forged carbon, the oxygen, the silicon, and the remaining helium, was ignited in a single terminal heartbeat. The star did not collapse into a singularity, it simply ceased to exist. Its entire body converted into a world-shattering blast wave that carried the first heavy elements out into the pristine vacuum of the Dark Ages. This violent death was the essential act of seeding the universe. The vacuum, which had been a sterile void of hydrogen and helium for nearly 200 million years, was suddenly polluted with the building blocks of complexity. The carbon that would one day form the basis of deoxyribonucleic acid, the oxygen that would fill the oceans of a distant Earth, and the silicon that would make up the rocky crust of planets were all cast into the void by these first suicidal gods. The population 3 stars were the ultimate donors, sacrificing their brief and brilliant lives to ensure that the next generation of stars would have the materials necessary to build a more stable and diverse reality. The III Atlas project, by tracing the chemical signatures of these first explosions at redshift 20, is documenting the very first instance of cosmic inheritance. We are seeing the moment the universe moved beyond its simple beginnings and began the long, complex journey toward the creation of a world. The path was paved with the wreckage of these first giants. Without their violent end, there would be no planets, no chemistry, and no life. Every atom of heavy matter in the modern universe can be traced back to this era of celestial martyrs, stars that burned with a fury that could not be sustained, so that the universe they left behind might one day have the chance to breathe. The landscape of redshift 20, as revealed by the III Atlas, is a realm of beautiful sterile terror. It is a universe defined by extreme gradients, where the cold, lightless voids of the intergalactic medium are punctured by the searing ultraviolet screams of the firstborn giants. There is a chilling indifference to this era. The cosmos is not a nursery, it is a high-pressure forge, operating with a clinical precision that is entirely unconcerned with the prospect of biological life. In this prehistoric theatre, the laws of physics are applied with a raw, unmitigated force, creating a reality that is fundamentally hostile to the very concept of organic complexity. The radiation flooding the early bubbles of reionization is so intense that it would act as a universal solvent for any complex molecular structure. If a strand of deoxyribonucleic acid were to be placed within the light of a population 3 star, it would be shredded in a trillionth of a second. The high-energy photons would not merely damage the genetic code, they would shatter the very bonds between the atoms, reducing the blueprint of life to a chaotic spray of subatomic debris. This was a time of hard radiation, ultraviolet rays, X-rays and gamma rays that saturated the vacuum, creating an environment where the delicate chemistry of a cell could never take root. It was a universe of fire and ice, a beautiful but lethal expanse where the only entities that could survive were those made of pure plasma or the crushed remnants of dead stars. The path at this stage was a gauntlet of radiation, a violent filtration process that allowed only the simplest and most resilient forms of matter to exist. Yet, this sterile terror was the absolute prerequisite for everything that followed. The very violence that would have prohibited life was the process that created the ingredients for it. We look back at the data from the III Atlas and see a landscape that is fundamentally alien, yet we are looking at our own prehistory. The carbon atom that currently resides in the valve of a human heart or the tip of a finger was likely forged in the centre of one of these suicidal giants. It was born in a furnace of several 100 million degrees, amidst the terminal collapse of a star 300 times the mass of the Sun. It was ejected into the void by a pair instability supernova, travelling across the expanding emptiness for millions of years before being caught in the gravitational pull of a second-generation star. The journey of these atoms is a testament to the endurance of matter across the vastness of deep time. From the chaotic, radiation-soaked environment of redshift 20, these heavy elements were recycled through successive generations of stars, each time becoming more concentrated and more diverse. They were incorporated into the swirling disks of gas and dust that surround infant suns, eventually clumping together to form the iron cores and silicate mantles of rocky planets. The oxygen we breathe today is a relic of that ancient violent forge, a gas that was once part of a primordial star's terminal breath. The phosphorus in our bones and the iron in our blood are the ash of a war that was fought when the universe was less than 2% of its current age. There is a profound contrast between the indifference of the early cosmos and the improbable existence of a human being. We are the survivors of a 13.8 billion year chain reaction, a sequence of events that began with the flickering ghost signals of the first galaxies. The hands that hold a telescope or a grain of sand are composed of the same material that once existed as a searing plasma in the Dark Ages. We are the unlikely outcome of a universe that spent its first few 100 million years trying to tear matter apart. By tracing the path through the Triple-I Atlas data, we are witnessing the transition from a state of sterile high-energy simplicity to a state of complex biological awareness. The early universe was not designed for us, yet it is because of its specific violent character that we are here. The chilling indifference of the Redshift 20 frontier is the backdrop against which the drama of life is set. It reminds us that we are a late and fragile addition to a very old and very dangerous story. The atoms in a human body have travelled through the most extreme environments in the history of existence, through the hearts of giants, the shockwaves of supernovae, and the cold silence of the intergalactic void, to finally settle into the delicate, organised structures that allow us to think, to feel, and to wonder. We are the point where the sterile terror of the first light finally finds a way to look back and understand itself, turning the ancestral shadows of the Triple-I Atlas into the light of human understanding. The discovery of the signal at Redshift 20 is more than a triumph of engineering. It is the closing of a cosmic circle. This flickering infrared ghost, originating from a time when the universe was only 180 million years old, serves as the first link in a chain reaction that has persisted for 13.8 billion years. The path revealed by the Triple-I Atlas is the definitive biography of existence, a narrative of increasing complexity that began in the absolute simplicity of the Dark Ages. It is a journey that started with the silent, invisible pool of dark matter, progressed through the suicidal brilliance of the first giants, and eventually culminated in the emergence of a consciousness capable of looking back at its own origin. We are the improbable heirs of a 13.8 billion year legacy, the final result of a universe that learned how to organise itself into the shape of a thought. This chain reaction was a sequence of narrow victories over entropy. It began with the dense dark matter halos acting as the first gravitational anchors, pulling the primordial hydrogen into the deep wells where the first light could ignite. It continued with the population 3 monsters, stars so massive and so pure that they sacrificed their brief lives to seed the vacuum with the heavy elements required for the future. It was accelerated by the direct collapse of gas into the first supermassive black holes, creating the gravitational engines that would drive the assembly of the first galaxies. Each of these events was a necessary step on the way to the present, a synchronized progression that turned a featureless soup of gas into a structured reality of stars, planets, and eventually biology. The realization that emerges from the Triple-I Atlas data is that the universe is no longer a blind machine. For billions of years, the cosmos operated according to the cold, indifferent laws of physics, a vast expanse of matter and energy governed by the relentless mathematics of gravity and nuclear fusion. But with the evolution of the human mind, the universe has achieved a singular and profound transformation. It has developed eyes. Through the gold-plated mirrors of our telescopes and the intricate neural networks of our brains, the cosmos is finally turning around to study its own beginning. We are the aperture through which the universe gazes upon its own infant face. Every photon from Redshift 20 that strikes a detector is a moment of cosmic self-recognition, a reunion between the light of the first dawn and the species that light eventually created. This perspective shifts the nature of our place in the heavens. We are not merely observers of a distant and disconnected history. We are the living embodiment of that history. The carbon in our cells, the iron in our blood, and the very electrical impulses that allow us to perceive the world are the direct descendants of the violent processes captured by the Triple-I Atlas. When we look at the data cliffs and the signatures of reionization, we are not looking at something other. We are looking at our own ancestral shadows, the prehistoric foundations of our own existence. The path is the story of how the universe grew from a state of sterile, high-energy simplicity into a state of sentient awareness, using the furnace of the first stars to forge the instruments of its own observation. The 13.8 billion year journey from the first flicker of light to the modern mind is a testimony to the creative power of the laws of physics. It shows that complexity is not an accident, but an inherent potential of the cosmos. By decoding the signals from the redshift 20 boundary, we're uncovering the rules of the game, the fundamental constants that ensured that a universe made of nothing but gas and dark matter would eventually produce a creature capable of asking where it came from. The III Atlas project is the latest chapter in this ongoing quest for self-knowledge, a mission that seeks to map the exact moment when the potential for life was first written into the fabric of space-time. As we stand on the threshold of this new era of discovery, the story of the universe continues to unfold before us. The data from the deep field is a reminder that the cosmos is far more efficient, far more structured, and far more interconnected than we ever dared to conceive. We have moved beyond the era of guessing and into the era of seeing, using the infrared threads of the first light to weave a more complete understanding of our origin. The journey that began with a single grain of sand held against the night sky has led us to the very edge of time, where we find not a void, but a vibrant and violent beginning that holds the secret of our own existence. The exploration of this path is a collective endeavour, a shared journey of the mind that transcends the boundaries of our small rocky world. To follow the III Atlas into the depths of the infrared frontier is to participate in the most significant act of recovery in human history. It is an invitation to witness the birth of the light and the shattering of the dark ages, to see the first gods of fire sacrifice themselves so that we might one day stand in the light of a modern sun. This is the narrative of everything that has ever been and everything that will ever be, a story that is still being written in the light of distant stars and the data streams of our greatest machines. To remain a part of this unfolding epic, to witness the next breakthroughs in our understanding of the cosmic dawn and the invisible scaffolding of reality, you're invited to join this ongoing journey. By subscribing and engaging with the search for our origins, you become a participant in the universe's own process of self-discovery. Together, we will continue to peer into the ancestral shadows, to decode the flickering ghosts of the first galaxies, and to follow the path wherever it may lead. The cosmos is turning around to study its own beginning, and through our collective curiosity, we ensure that the light of understanding will never again be lost to the dark. Join us as we continue to explore the history of the universe, one photon at a time.